We're going to be diving into the idea of what is a set and what you can do with sets and why they're important and why they're useful. And believe me, this is a huge, important thing to understand in the world of discrete structures and the world of computer science. So we'll take it baby step. This is a list of all the things we're going to cover today, guys. It's a lot of stuff, all right? There's no need for me to read the list there. You can look at it, but we're going to hit every topic on the list there, okay? So the first thing, let's take a look at what exactly is a set, all right? It's a collection of stuff, right? It's just a collection of things. If you've taken 1410, you're familiar with the collections, the Java collections class. Or is it an interface? I can't remember now, but anyway, you know what I'm talking about, right? The collections. It's the same idea. There's actually some set, sort of in the background, sets are involved. There's the hash set data type that you're probably familiar with, the hash set class, okay? But here's an example here. Here's a sample. It's banana, apple, and orange. What's that probably a set of? Fruit, right? Sample set number 2, a quarter, a chicken, and a paperclip. What's that a sample set of? Things you can eat. Oh my gosh. If you're 5, right? Yeah. Nice. That's hilarious. Yeah, it's just it's a sample of stuff. All right, it's a sample of stuff. It's just anything. The point in showing you that second set is they don't have to be related to each other. They don't have to, they can be totally weird, different, unrelated things. Typically they're not, but they can be, all right? So let's take a look at some of the basic properties of a set. This is just to give you a foundation so that the other stuff moving forward will make some sense. Take a look at the first one there. A banana, orange, apple set is the same as an orange, banana, apple set. It's the same. The order is irrelevant. Now, if you recall in 1410, you have a hash set, and what's the other one that kind of goes hand in hand with it? That's not the one I'm thinking of. That's one, but not the one I'm thinking of. Not maps. There's only one left, I think. Starts with an L, ends with ist. That would be a list. Right. List set. You guys familiar with that? What's the difference between a list and a hash set?
A list can have duplicates.
Yeah, a list can have the same thing in twice. And if you, in a set, you try to add to a set something that's already in the set, it will not add it, right? It will not do it, okay? That's just the way the class is designed. So obviously the set 1, 2, 3, 4 is the same as 2, 3, 4, 1. But look at the third bullet point there. The set 1, 2, 3, 3, 3, 4, 5, 5, 6 is the same as 1, 2, 3, 4, 5, 6. Just like a hash set in Java, the duplications are ignored. They're not counted. You wouldn't do it that way, okay? So there's this idea, this concept called cardinality, and what cardinality is, it's basically how many unique elements are there actually in the set. So it's not typical for you to see a set that looks like that, where you have duplicates like that. That's just me to demonstrate the point. And we will do a few more like that to make sure we have our heads wrapped around that concept. But the cardinality is how many unique numbers are there, or how many unique items are there. And in the case of this set 1, 2, 3, 3, 3, 4, 5, 5, 6, there's only 6 unique distinct items, okay? So the cardinality is 6. And as you can see, the cardinality, banana, apple, orange, kiwi, lime, orange, twice. The cardinality is just 5 because there's only 5 unique things, right? Make some sense? So representing sets. There are 2 ways to do it. And the first one we're going to look at is what's called roster notation. And roster, it's just what it sounds like. When you think of a roster, what word pops into your head? What things pop into your head? What do you think of? Yeah, a sports team roster, right? What is a sports team roster?
Just a collection of athletes.
Yeah, just a list of the athletes, right? Their names, or a collection. That's a good term for it too, right? So roster notation just literally lists the items in the set. That's all it does, right? So it just simply lists the items, right? So this is typically the form that it would take right here. You start with a capital letter, and you would call that, this is called set A. And it's equal to curly braces, and the curly braces are part of the syntax, banana, apple, orange. And then set B is equal to quarter, chicken, paperclip, right? Things you can eat. Man, it's hilarious. Okay, all right. So the other thing is you can use an ellipsis to generalize a list. For example, C. What do you suppose C is representing there? Yeah, letters A through Z, probably, right? And the ellipsis is used when it's not meant to be tricky. It's not meant to trick people into thinking it's the alphabet, but it really is something else, right? It's when it's obvious what you're talking about. So what do you suppose set D is representing?
Negative infinity to infinity.
Yep, negative infinity to positive infinity, right? Or to infinity. How about E?
Negative infinity to 3.
Yeah, negative infinity up to the number 3, okay? So that's a way to generalize it, but this is just representing it using roster notation. Pretty simple way to do it, all right? The next one is set builder notation. Now the idea of set builder notation is to describe the properties of the set in using symbols and mathematical notation or just actual words. So these are useful for really big sets, and they're also useful in really easily definable groups that you can describe the properties of pretty easily. Yes, sir.
So could you do the ellipses, like if you wanted to go like 0 to 200, you could do 1, 2, 3, ellipses 200?
Yes, you could. So the question was, let's open up a thing here because I noticed when I'm editing these videos, I can't hear your questions on the recording very well. So the question is, if I wanted to make a set of 1 to 100, I could do this. Or 200 or whatever, and that's totally legitimate, yeah, for sure.
You have to put the spaces in between the dots.
That is the official grammatically correct way to make an ellipsis. An ellipsis is defined as a space, period, space, period, space, period, space. That's just the grammar English way to do it, yeah. All right, but if you didn't, people would know what you meant, right? But if you wanted to be grammatically correct, you would do that. So here's an example. We're gonna have a set called O, and this is the notation here. O is equal to the set X, then that line there means such that. That's the pipe symbol, which is on the key that's above your enter key, probably, most computers. So O is a set of X such that X is an odd positive integer less than 10. That's how you read that, okay? X such that. Get that in your brain that that line means such that, okay? That's not to be confused with the logical or operator in Java or in other programming languages, okay? Or the bitwise operator or either. So when it comes to doing set builder notation, there are a lot of symbols that can come in handy, and so we're going to walk through a whole bunch of them, all right? So this one is what's called an element of a set. It looks like an E, and so it's pretty easy to remember. I'm pretty sure this is Greek alphabet here. But that is the letter E, and it stands for, or looks like the letter E, and it stands for element. And we'll see some examples in just a moment. This means not an element of the set, right? Can you dig that? That makes some sense. This one means it's a subset, okay? So there are, I don't know, about 15 people in the room right now. Any one of you, or any, like let's pick one table here. There's 3 people at this table. These 3 at this table are a subset of this entire set of people in this room, right? What's another subset is that table, or that table, or that table. Another subset, though, that's maybe a little less intuitive is the entire room itself. The entire room is a subset of the entire room, right? So a subset can include the original set. The original set is a subset of the original set. Does that make sense? Okay. And then, of course, this, now notice the slight difference here. Not a subset of the set. Notice the underline is missing there. See that? This means not a subset. Now you can think of this underline as sort of like the greater than or the less than or equal to kind of a thing. Okay? A subset is less than the whole set or equal to the whole set, right? You can kind of think of it that way. Not a subset, though, it's just not at all. Like I'm talking about somebody in that room. They're not a subset of this room, right? Now, typically when we think of a subset, we think in our brains, well, that's not the whole set. It can't be the whole set. That doesn't make any sense, right? That's the way our human minds work. Well, in the world of math, there is a term for that as well, which is called a proper subset, which is notated by this guy right here. Okay, that's just so it looks like a less than symbol, right? So what you would think of like in the human world is a subset where it's not including the original group. That's what we call that a proper subset. You dig it? Okay? All right. Questions about the basic set of symbols there. We're going to look at examples on the right so that we can understand what these, what they look like and how they're used, okay? So the first one here. 2 is an element, that we're using this set up here, by the way, I should point that out. That here we're using set A, right here, okay? That's our set that we're looking at. And we're saying that 2 is an element of the set A. 3 is an element of the set A. Make sense? Yeah? Okay. Next up, 10 is not an element of the set A. Beavis is also not an element of the set A. Okay, pretty simple, straightforward. Look at this one. I'm claiming that A is a subset of the set A. So in other words, 1, 2, 3, 4, 5, 6, 7, 8, 9 is a subset of A. Isn't that the original set? But as we pointed out, that is a valid thing, right? So A is a subset of A. 1, 2, 3, 4 is a subset of A. Pick any number in the list, that's a subset of A. And then I've just written out the whole set. 1, 2, 3, 4, 5, 6, 7, 8, 9, that last little bracket there, that is exactly the same thing as A. That's the same thing, but it's also a subset of A, okay? That's one of the trickier ones to wrap your head around, but it's not super hard. You feeling okay about that? Okay. 10, 12, 13 is not subset of A. Look at the next one, though. 1 and 3 are part of A, aren't they? But 12 is not. Therefore, that set is actually not a subset of A, right? Even just because it has some common elements, it's not actually a subset. In order for it to be a subset, the definition of a subset, listen carefully, is everything in the subset is also in the original set. That's the definition of a subset, okay? Last one. This is a proper subset, right? 1, 2, 3, 4 is a proper subset of A. But just a minute ago, I also pointed out that that's a subset of A. It is a subset and a proper subset. Dig it? Okay? 4 and 5 subset, 8 is also a subset, okay? This is a very important thing to understand, and we have a whole section in the lecture today, and it's also going to be the basis of our whiteboard exercises, and probably be the split point where I split the video into two, about the difference between an element of and a subset of. That's really tricky at first, okay? It takes a little bit of practice. Okay, so make sure if you see any immediate questions here, we feeling okay? Yeah.
Can't you have an empty set or a set with a single item?
Oh, we got a whole chunk of slides about the empty set too, yeah, for sure. Yeah, the empty set's probably, of all the stuff we're gonna cover today, is definitely the trickiest, the empty set, okay? And we're gonna see some examples of that, actually using a live database too, to make some sense out of that, but yeah, we will get to that for sure. So these are just some examples of potential subsets. The empty set is also a subset. Bless you. All right, so no questions here? No? All right. Take a look. I'm going to leave those set symbols on the left to remind us. Normally I'd have those written on the whiteboard and they just kind of stay there throughout the day. So I'm going to leave them on the screen as many slides as I can without getting in the way of the other stuff. But we're going to now look at the mathematical set notations. There are several sets that are just defined in math that we will be using in our set stuff, right? What are some sets of numbers or things that we can think of in math that we know about?
Integers.
Yeah, set of integers, right? Okay, there's a whole bunch of them here. The first one we call the set of natural numbers, okay? It's represented by this sort of like a double N is how they refer to it if you see it written, but it's just a fancy looking N. And the set of natural numbers, you can see what the set is, right? It's 0 through infinity. But what is it? What does that mean, a natural number?
Positive integer.
Yeah, it's a positive integer. And why is that called a natural number? Why do you suppose we give it that name?
Because that's what you do when you count things.
Yeah, exactly. I can't have, putting aside like maybe possibly your bank balance, right? You can't have a negative amount of things, right? Like there's not a negative number of tables in this room or people. There's going to be either no people or some people, but not -3 people, right? So it's a natural number when you're counting things into discrete groups, you're counting things, it's a natural number. All right. The set of integers. Why didn't we use I for integers? I is for imaginary numbers, right? So the set of integers, as you can see, goes from negative infinity to positive infinity, and it's whole numbers, okay? So negative there's not, we're not counting no, we're not counting fractions. Sorry, I couldn't think of the word. Okay. All right, so that's simple enough. We also can represent just the positive integers with a z plus. You'll see it in that notation. You also see it in a fancy weird notation that'll say that the set is x such that x is an element of z and greater than 0 or something like that. That's another way to notate it. But these are both legitimate. And you technically can put a z minus, but you're less likely to see that notation. Again, you'll see the notation that says the set of whatever is x such that x is an element of z and x is less than 0. That's more likely the way you'll see it. Then we have the set of all real numbers. What's a real number?
Number that's not imaginary.
Yeah, it's not imaginary, right? And it's a fraction. Fractions are in there. Everything's in there. Irrational numbers are in there, okay? All right. And then we can also represent it as positive as well. And you could do negative if you wanted to, but these are typically the ones you'll see the most of, right? And again, notice these letterings. They're just a double R, double Z, double N, whatever. Then, of course, imaginary numbers. And we're not going to get into that, what they are. There's a link in the modules that talk about that, which is a really cool resource. There's a really great website called mathisfun.com. You ever go there? It's really cool. Yeah. Yeah, it's a cool site. I think it's meant to explain it to like younger kids, which is great for my brain. And I read them like, yes, I can understand this. Yeah, it's cool. Then we have the set of rational numbers, which is Q. Why didn't we use R? Because it was already taken for real numbers, right? We just picked the next letter up, Q. And this, we know this definition, but look at this notation here. This is set builder notation. Q is equal to P over Q such that P is an element of the set of integers, and Q is an element of the set of integers, and Q is not equal to 0. That is a definition of a rational number. We talked about that the other day when we did the square root of 2 being not rational proof, right? Okay? And you can do Q plus and Q minus if you'd like, okay?
Are we going to use any of these mathematical set representations in order to define domains in any of our?
Oh, very often.
So, okay,
Yeah,
this is domain definition.
yeah, they could be a domain, yeah. They're not, I mean, yeah, typically that's how you'd use it, as a domain definition. And we have in the past several times where I've said the domain is all integers. I just didn't write the Z on the board because you guys didn't know that terminology yet. But yeah, we can definitely do that. There's one more. Anybody know what it is? There's more than one. Yeah, what is it, Chad?
Complex.
Complex number, yeah. That's a C, the set of complex numbers. What is a complex number?
Takes the form of x plus I, y.
Yeah, what does that mean though in like human terms? That's a very math answer.
Well, it's basically in the complex plane, so it's any type, it's so you can represent almost any type of number.
Yeah, what happens if you have an imaginary number and you do math with a real number on it? You can get complex numbers, right? You can get what's called a complex number.
With the complex numbers, you can do calculus and derivatives and integrals with
Yep.
them on
Yeah,
equations you didn't normally could, like
yeah.
I to the I power.
Yeah, it's very useful in calculus and derivatives and integrals and things like that for sure. We won't really get into the uses of it here. We don't really deal with imaginary numbers or complex numbers in here, but all the other ones we will for sure use. There's a really cool Venn diagram coming up on the next slide that shows you which of these sets are subsets of other sets, right? So take a look at this. Complex numbers covers all numbers. Then notice the imaginary, I just found this slide, this image online. Technically, the imaginary number should be a lowercase I there, but I didn't want to try to edit the picture. But natural numbers, like the numbers 1, 0 through whatever, are a subset of all integers, agreed? And integers are a subset of all rational numbers, because an integer can be represented rationally, right? What's the ratio for 3? 3 over 1, right? Okay, rational numbers, that's anything that can be represented as a ratio or a fraction. And then a real number, well, irrational numbers are real, right? So that would be the stuff that's sort of in this little green area here, that's not in the Q, right? And then again, complex numbers cover everything. So this is a good slide that's in the condensed version for you guys as well. So take a look at that, and that's a good way to represent these things, okay? Okay, so any questions so far about anything we've covered? The whole idea was to sort of somewhat spoon feed you some definitions and some ideas of what's going on with a set. But now we're going to look at some applications, all right? But we needed to make sure we kind of understand the vocabulary. Are you feeling okay? All right. So again, we have the roster notation on the left. We got the set builder notation on the right, just to remind us how to use this, okay? So let's take a couple examples of an application here. If you'll recall, in Java, you have data types, right? You have the 8 primitive data types. You guys remember what they are? Shout them out. Boolean. Actually, int, right? Integer's different. Double, float. String is not actually a primitive data type, it's a class, but it's a very common one for sure. Char, a string is a group, a bunch of chars, yeah. What else? What is it? Oh, byte, yep. Long. And what was the last one? Short, yep. There we go. There they are, right there. Byte, character, or char, excuse me. Boolean, short, int, long, double, float. These are sets. What is Boolean the set of? True and false, or 1 and 0, depending on your language, right? JavaScript, you can use, this Boolean is 0 and everything else in the entire universe, right? In JavaScript, 0 is false, everything else in the entire universe is considered true, okay? So here's all of the definitions here, and don't memorize this, don't write this down. This is, you've seen this, you can look it up in the Java documentation. This is not a Java class, but it's good to see how this applies to something that you're familiar with. So again, Boolean is a set of true or false, or 1 and 0, right? Character is a set of all characters, right? What's a character? Capital A through Z, lowercase a through Z, the numbers 1 through 0, or 0 through 9 or whatever. The minus sign, the plus sign, the dash, the slash, the comma, the quote, the equal sign, all that stuff, right? That'd be a big thing to write out the list there. So we're just saying set of all characters. A byte. Now the difference, just since you brought up unsigned, in C++, you can choose, do I want my variables to be signed or unsigned? So if, take an int in Java, you can see on bullet point 5 there, it goes from -2 billion to +2 billion, right? In C++, you can choose to go that route, which is signed, negatives and positive, or unsigned, which goes 0 to 4 point whatever billion that would be. Still the same amount of numbers, it's just the range changes a little bit. Java, you're stuck, it's always signed, okay? And then again, you can see the short, that's its range there. That's the highest number and the lowest number that a short can hold, an int, and so on and so forth. Notice now looking at float, long's big, right? That's humongous. Float has a very specific definition there that's really hard to kind of represent with actual numbers, but this is a set builder way of representing it. You're just describing the properties of what's in the set, okay? So big picture, that's just one simple example of sets. Databases are built on sets. There, if you know anything about databases, if you know what a join is basically just set operations, right? Unions and intersects and this kind of stuff, okay? All right, so any questions about that? That's a simple application. We'll see some examples more in a few minutes, but we okay here? All right. So a couple more properties that are interesting. This is the slide we already looked at. We're going to add a couple things to it. Look at our red little notation there. Somebody want to give a shot at reading that? You got to get real familiar with that notation, guys, for sure. Just pronounce it. Like, don't worry about like understanding the full meaning, but see if you can just pronounce it. Yeah, for all x in whatever the domain of x is an element of A if and only if x is an element of B. So what does that mean? That means that A is equal to B, right? That's how we can, A is equal to B if this statement is true, right? If set A and B are the same, then that statement will be true. Make sense? So sets can contain other sets too, and this is where it gets nasty, all right? So for example, this is a legitimate set here. Orange, banana, and then the set of apple and orange, and then the set of orange, banana. What's the cardinality of that? Remember, cardinality is how many unique items are in the set. I hear 4. I I heard a couple fours. Anybody have a different answer? One that's, he says 3, interesting.
Yeah, I was like 3.
3?
I feel like-
Oh, well, anybody want to change their answer? 5. 32, whatever, yeah. Nice. What counts as cardinality is everything in the, we're using a bag as a metaphor a second ago, everything in the bag. So imagine every curly brace there as a bag, right? There's one outer bag that contains orange, banana, then another bag, and then another bag. So there's 4 things in the outer bag. Those 4 things are the elements, the unique individual elements, and they are, that is the cardinality. There's 4 unique things, okay? Make sense? Yeah.
If the two bags contain the same thing, would the cardinality be 3?
Good question, yeah. So the question was, if the 2 bags, one's got apple orange, the other one's got orange banana, what if they both had apple orange? Then the cardinality of that whole outer bag would only be 3, right? Because a bag that contains apple orange is the same as a bag that contains apple orange. So they're not unique items, they're the same thing. Very good.
So if we were to change that banana right there to something like kiwi though, it wouldn't increase the cardinality of the set, because the outer set can't technically see inside of the inner.
That's correct. So if I were to change either this banana to something else or that banana to something else, it would have no bearing on it, because what the elements of this bag are that's element number 1, if you will, that's element number 2, that's the 3rd element, and that's the 4th element right there, right? So there's 4 elements that are unique, distinct elements inside the bag. Make sense? All right, other questions? Okay,
I have a question.
yeah.
So if you had orange banana, instead of orange banana, if you had orange, would that just condense to orange and then you
Yeah,
just have?
yeah, that's what I thought I had done in the slide, yeah. So the question was, what if instead of having orange banana here, like orange, banana, what if this banana right here were also orange? Then the cardinality of this set would be 3.
Oh, no, like that, you see the subset of.
Oh, yeah.
orange Banana, like the far right.
Oh, okay, so,
That's
so if,
orange and orange.
actually,
That
okay,
condenses
good.
to an orange, and then-
Yeah, so if that were orange instead of orange banana like it is right now, the cardinality of the outer, the main set, is still 4. It's still 4, yeah.
So you can't put orange, condense that to just be orange. one.
You would, but the cardinality of that little set would be 1.
Okay.
But the outer set, because remember, this, whatever's in this bag right here, there could be 1 thing, 10 things, a million things, it's irrelevant. It's just that bag itself is 1 element of this bigger bag here, right? Yep. So if I had 2 inner bags that had identical content, then that eliminates 1 bag. But if whatever's in the content, as long as the inner bags are different from each other, regardless of, now, this 1 inner bag, like I said earlier, might have 20 caramels in it, its cardinality is still just 1. But the bag itself man, this is so hard to explain in like words that without a whiteboard, man. So let's go back to that metaphor again. We have 1 big bag, grocery bag, like a big one you put your groceries in. In there is 20 caramels, 10 peppermints, and 3 butterscotches. Cardinality of that bag is 3. If I add to that bag a little lunch sack that has 20 caramels in it, what's the cardinality of the big grocery bag? 4. What's the cardinality of that little teeny bag inside? Just 1. Does that make sense? Yep. Okay, we feel okay about that? It's tricky stuff, guys, for sure. Yeah. All right. So, questions? Doing all right? All right. It just reminds me to ask, because I'll forget. Yeah. All right, so let's talk about the empty set. Dun, dun, dun. Okay? The empty set is Mr. Tricky Pants is what I like to call him, because he is weird, okay? All right, this guy is confusing sometimes. It can be represented with a null symbol. That's not a 0, that's a null. We call that a null, even though that's how I do write my zeros, that's a null. Or it can be represented as an empty set of curly braces. It's like an empty paper bag, okay? Both of those are exactly the same thing. They're just 2 different ways to notate it. It's also known as the null set. Empty set, null set, same idea. A couple things we need to understand about this. Thing number 1, null is different from that little picture there, which I don't want to pronounce how you say it just yet. I want to see if you can figure out, how would you pronounce that last little piece there?
The set that contains the null.
It's the set that contains the empty set. Very good. The set that contains the null set. Yep. So the first thing on the left there is just the null set. It's an empty set. The thing on the right there is the set that contains an empty set, right? Okay? Tricky. The null, again, that's an empty set, and that is a set that contains an empty set, okay? Make sense? All right. That, so in other words, this, right here, it's the same thing as this, just a different way to notate it. One of those will make more sense to your brain than the other, right? And it'll be different for each of you. Sometimes when we get into some of these problems with this, it helps to think of it both ways and see if one of them clicks a little bit more, okay? This will be important, as we'll see, and we're going to look at some database stuff in a minute. All right, any questions about that? Good. Now, the null set, the last bullet there, is a subset of all sets. The empty set is a subset of all sets. Let's take this room again, okay? Chad is a subset of the people in this room, right? Steen is a subset of the people in this room. Ashish, you're a subset of the people in this room. Steen, Ashish, and Chad, that's another subset of the people in this room. Also, nobody is also a subset of the people in this room, right? If I said pick a person in the room, any person I pick is a subset. But if I decided to choose nobody, that is also a subset of the people in this room. So every set has a subset of the null set. Now the null set, listen carefully to this, the null set is not an element of any set, necessarily, of all sets. It could be, for example, the null set here is an element of this bigger set, right? In that scenario. But that last bullet point that says the null set is a subset of all sets is not the same thing as saying the null set is an element of all subsets. You dig that? Does that make sense? It will in a minute when we look at sets of chickens. In just a minute, okay? All right. To the code. Okay. Trying to add sound effects, make it more exciting here. That was the bat symbol transition for the old Batman cartoon. So here's a real database right here. Don't worry if you don't know database commands, it's totally irrelevant. I'm just gonna do a couple things here real quick. This is for my 1550 class. We have this database called the TAL database, and what it does is it's a company that distributes toys. It's a toy manufacturer, and so just quickly you can see the tables here. There's a customer table, an item table, which is the products, the orders table, and then the rep table, the order line. We're not going to look at that. Okay. So if I want to see all the sales reps, I can look at the sales reps. These are the sales reps. Okay. There are 4 of them. Notice what the final little line there says on the command line. What's it say? Not MySQL. What's above that? 4 rows in set. In the set. This is a set of the entire database. It's all the records in the set. Okay. Now I could say this. Select star from rep where let's do rate is equal to 0.06. Oops, for my semicolon. Now I have 3 rows in the set. Those 3 people are a subset of the original set, right? Okay, what if I say this? Select star from rep where rep num is in 15 or 45. That is a subset of the original set. You dig it, right? All right, so how about this? Select star from rep where rep num is greater than 70. I got the empty set. That empty set is a subset of the original set. I ended up selecting nothing from it, but that is a subset. But notice, here's the original full set right here. Notice here, there's no empty set in here, right? There's no empty record. Okay, empty is not an element of the table, but it's a subset of the table, right? Element versus subset, very critical concept to wrap your head around. Questions about that idea? Okay. To the whiteboards. This is where we'll pause the video, but I'm going to put this on the screen first. Okay. We're going to be looking at understanding the difference between elements and sets, subsets, I should say. And so we're going to solve all of these problems. I'm going to pair you guys up and have you take a look at those in just a moment. All right, so hopefully you paused the video if you were watching it, not live here, and you took a shot at these. Let's walk through them, and your answers are still on the whiteboard here for those here in the classroom. Look at the screen and compare what I'm going to show you to what you have on the whiteboard. Looks like, bless you, looks like everybody got all the same answers except there's one answer that was different on this team here. We'll see who's right or wrong when we get there in a minute. What's good though is that you all, and I haven't looked at your answers to know if you're right or wrong yet. So either, the fact that you guys all pretty much got the same answer tells me either you guys all got the same wrong answers, or you got all the same right answers. If you got all the same wrong answers, that means I screwed up explaining it to you. If you all got the right answers, hopefully that means you're understanding it pretty well. So let's take a look at the first one. Chicken, A is the set of chicken and the set of chicken, right? It's the set that contains chicken and the set that contains chicken. And then B is the set that contains chicken, the set that contains chicken, and then chicken, right? Obviously, if we condense that down, what does B look like? Same as A, right? It's exactly the same. So the answer to is A equal to B, true, right? So check your answers. I think everybody got that one correct. Okay, true or false is, and I'm not going to say it out loud because if I say it out loud, the answer will become obvious. So what is the second one asking there, number 2?
Chicken equals the set.
Is the element chicken equal to the set that contains the element chicken? And the answer is false. Very good. Okay. I hate when the font sizes change on between slides. It bugs me. Okay, next up, bullet point number 3. We have 4 questions. So first question, is A an element of B? That's what that question is asking. Is A an element of B? What is A? The set that contains chicken. Is the set that contains chicken an element of B? It is, right? See that? It's readjusting again. It bugs me. I think it won't do that anymore. I thought I fixed all those, but I guess I missed one. Is A equal to B? No, because A is a set. B is a set that contains a set, right? It's different, right? So the answer to that is false. Stop shifting. All right. Next one. Is A, how do we pronounce that one?
A subset of.
Is A a subset of B? Is it?
Yeah.
All right, I'm looking at the board to see what we have here. This team put true. That team put true. What'd you guys put over there?
True.
It is not. So let's think about this. A subset is defined as everything in, let's go with A being the subset, everything in A is also in B. Okay? A is a set. What is in the set A?
The element chicken.
Just the word chicken. Is just the word chicken an element of B? It is not. The only element of B is the set that contains chicken. That make sense? So A is not a subset of B.
Because when we're saying A, we're assuming just the elements inside of it, not the.
No, that is, if you put true, that would have been your assumption. But A is the set chicken, the set that contains chicken, right? It's a set, right? A is a set. When we look at power sets in a few minutes, then this will maybe clear things up a little bit. If I were to say, give me a subset of everybody of this room here, I could put each one of your names in a bracket, right? It would be the bracket is the set, and then your name that's the subset. That would be a subset of the big brackets that contains each one of your individual names, right? There's 20 names in the brackets, and then I take one out and put it in curly braces. That is a subset. A is a set. Agreed? That is a set. The set A contains one element. What's that one element? chicken. B is a set. B contains one element. What is it? A set that contains, who cares what it contains, but it contains chicken, right? So A is not a subset of B. Okay?
So if B only had one curly brace, that would be true, rather than two stacked.
Yes, very good. Yeah, if B only had one set of curly braces, then yeah, it would be a subset, but it would not be a proper subset, right?
Correct.
Yep. All right, so with that being understood, that the third one there is false. Is everybody on board with that? We all making sense of that? Okay. Does anybody want to change their answer for number 4? Everybody puts, or the fourth bullet point of number 3. Everybody put true. No, these guys put false. Did you guys put true over there? I can't see.
Yeah, we true.
So this team put false, the other two put true. Anybody want to change their answers? Answer is false. It's interesting that you got that one, that you guys got that one, but missed the one above it. That's interesting. It's tricky stuff.
If you assume if you assume the first one is true, you would think that if your set is the entire thing, like how 1, 2, 3, 4 isn't the proper subset.
Yes, good
That's
point.
kinda what we thought.
Yeah, good point. Yeah, so the answer that is false. So this is why I do this exercise, because it's very, very tricky to distinguish the difference between an element of and a set of. So that's why on number 3, that the first bullet point there is A, an element of B, is true, right? A is a set. Well, B has an element that is a set, right? A is an element of B, but is not a subset, right? Follow that? And if you're not following that, and you, A, read the chapter for sure, chapter 2.1, and B, look at these slides and study them, and make sure you can wrap your head around that, okay? All right, next up, number 4, the first bullet point is A, an element of B. I think everybody put true on the boards. Yeah? Yeah, it's true. Okay, A is an element of B. That's exactly the same thing basically as number 3, right? It just so happens that this B on number 4 has 2 things in it. Okay, is A equal to B? A is not equal to B, because A is chicken, B is chicken and the set that contains chicken. So in other words, B is a thing and a set, right? Which is also a thing, but it's a different thing, right? One's a chicken, one's a set, okay? So the answer to that one is false. All right, is A subset of B?
True.
I hear true. So what are the 2 elements in B? Chicken, and then the set chicken, that contains chicken, right? So any one of those things individually is actually a subset, right? So in this case, yeah, chicken is one of those things. So I have a set that contains just chicken, that's a subset of the B, right? Because all the elements in A are also in B. Now look at this closely, guys. This is tricky. The question I have for you is, what makes this a subset of this? Which component is a subset? Is it this piece or this piece that we've pulled out and made into a separate set? The first piece, right? We made a set that contains this one element right here, right? Does that make sense? Okay. All right, so if that's the case, then what is the answer to A being a proper subset of B?
True. Be true.
Why is it true?
They're not equal.
And it's a subset, right? Yeah. So if the third bullet point there under 4 is true, then the fourth one is true if the sets are not equal to each other, and they are not equal to each other. And so all elements are in A are in B, and A is not equal to B. Dig it? Okay, last one. We have 3 sets. S is A, B, C, D, T is 1, 2, 3, and then U is B and 2. Is the set that contains A an element of S? It is not, right? I'm not asking if A is an element of S. I'm asking if the set that contains A is an element, right? Make sense? So if there were curly braces around this A right here, then the answer would be yes, okay? All right, good. I think it's starting to sink in a little bit, okay? So the answer is false. Now that's a number 1 there. I don't know if you could tell this font's funny. It looks like an L or something. Is 1 an element of T? Yeah, that's pretty straightforward. I think that one makes some sense, okay? Is B comma 2 an element of U? How many people, did everybody put the same answer? It looks like you all did. The same correct answer. The answer is false, right? Because the set that contains B and 2 is not an element of U, right? Make sense? We good on that? You guys all got the correct answer anyway, so we're good, yeah.
So just to make sure I fully understand it, let's say we put another outside brace around number 3, A is equal to the set that contains chicken.
Wait, sorry,
So
over.
if we were to put another curly brace.
Hold on, let me get to where we're at. You're talking about right here?
If you were to put, yeah.
Okay.
The set A, if we were to put another curly brace around that, that would change all of them to false except for the third one.
Okay, so the question is if I put another curly brace around it, so in other words, it looked like this,
Yeah, they both
okay?
look the
They
same.
look like that, then the first answer is A, an element of B, would be no, would be false. A equal to B would be true, right? They'd be identical. A subset would be true, right? Proper subset would be false. Yeah, good. Good question. All right, other questions. So the power set, this will maybe help clarify some of those set versus, element versus subset, okay? So here's the idea of a subset, or a power set. It's a set that contains all of the subsets of a set. Now this room with 15 people or whatever in it, each one of you individually is a subset. Then any pairing of any 2 of you is a subset, right? You and you, or whatever, right? Or any pairing of 3 of you, or that's not pairing, but grouping of 3 of you. Then any grouping of 4 of you, right? So I could pair Jace with any 3 students, and then I could pair Brian with any other 3 students, right? And so on and so forth. Those are all completely different groups, okay? So all of those sets, when you add them all, you put all of them together, and you put big fat curly braces around all of those, that's the power set, okay? How many subsets would there be to this room? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Count me, there's 15 people in here. 2 to the 15th power, whatever that number is, that's how many elements will be in the power set of this classroom, right? Okay, let's take a look at some smaller examples here. Let's go with the set A, it contains 1, 2, and 3. What's the power set of that look like? There'd be 8 elements, okay? And there would be, the set would contain a set that has 1 in it, and it would have a set that has 2 in it, and so forth, right? So it would look like this. So this big outer one here is the power, and this is how we notate it, right? The power set of A, that's how you write that. But this big curly braces right here, this one on the edge here, that is the curly braces for the power set. Everything else in it is elements. Well, those elements all happen to be sets, right? So in this case, the power set contains a set that contains 1, a set that contains 1, 2, a set that contains 1, 3, a set that contains 2, and so on and so forth, right? And you'll notice the last 2 here, one of them is the empty set, and one of them is the entire original set. Bless you. That's the power set, okay? How do we feel about that big picture-wise? Does that make some sense?
Wait, I thought that empty set couldn't be an element.
Nope, that's not what it, see, very tricky, right? That's why I call it Mr. Tricky Pants, okay? So, it can be, but it's not always. So the original statement was the empty set is always a subset of every set. But the empty set is not necessarily an element of every
So
set,
it's not always, okay.
right? It can be, but it isn't always, yeah. So, you know, and you'll notice that very thing, right here, this set here, it does not contain the empty set. An element, the empty set is not an element of that. But the empty set is a subset of that, right? Right, make sense? Yeah.
So the empty set is not always, but can be an element of a set, but it would be, you would see it in the original set.
You would see it.
But it is always a subset
Subset.
of every set.
Yeah. So the question was, the empty set can be, but is not always, an element of a set. And if it were an element of the set, you would see it in there. Like the blue box I have right there, you cannot see an empty set in there, therefore it is not an element of it. That is correct. But the empty set is always a subset of the original set. The reason being is because any group of things, any set of things, I can choose to pick 1, 2, 3, 10 of them, or none of them. If I choose to pick none, my resulting choice is an empty set, right? Just like that database query we did a minute ago. I chose everybody whose number was greater than 70, which was nobody. Yeah.
So is the empty set a subset of the power set?
Yeah. Yes, because you're right. Yeah, doing a power set on a power set, right? It's kind of messy, but yeah. Yeah, so the empty set is a subset of the power set. The empty set is a subset of every set, okay? So the power set of the power set would be really messy to write, and maybe I'll write one out and show it to you guys, but it'd be,
Power of 8.
it would still be 2 to the power of 8, right? But it would be everything in there paired up. So it would be, one thing would be the set that contains the set that contains 1, right? And then another one will be the set that contains the set 1, 2.
Oh, okay, so the other question I have.
That's right.
Since there is an empty set inside of the power set, then the empty set is an element.
It is also an element, yeah. So the empty set is always a subset of every set.
Yes.
Therefore, it is a subset of the power set. But in this case, the power set, the empty set is also an element of that set, right? Every little thing in there is an element of that set. Yeah.
So every power set will have the empty set as an element.
Yes. Every power set will have the empty set as an element. Because the power set contains all subsets of the original set. And because the empty set is always a subset of all sets, that's a lot of words there, right? Does that make sense? Yeah, okay. Tricky stuff. Okay.
I just want to write a program that takes the power sets of power sets.
It just recursively does that. That is crazy. Okay. So, again, it's going to be the number of elements in the set is n, and the number of elements in this power set is 2 to the n, all right? And there's a really cool link in the resources section that goes to that Math is Fun page that shows a little correlation to how the power set relates to binary numbers. It's really kind of a cool little thing, but we're not going to have time to go through it right now. All right, so here is a question for you. What is the power set of the empty set?
Empty set.
Yeah, this is a tricky one.
1 to the power of 2 is 1.
Well, first of all, how many elements are going to be in the power set?
Okay, well that's nothing.
So there's no elements in the empty set, right? It's empty. So what's our rule? 2 to the n? What's n? 0. So 2 to the 0 is? 1. So there's only going to be one thing in the power set. What is it? It's the empty set, right? Yeah, it's the empty set. 2 to the n is 1. And the power set of the empty set is the set that contains the empty set. Yeah. Okay, can you see that? And I just wrote it in 2 different ways, right? They're the same thing. Pick whichever one your brain likes, that or that. They're the same thing, okay? But that is the power set of the empty set. Because remember, listen very carefully. If you're a note taker, I would suggest for just a split second, you don't take any notes, you just give me all your focus for just a split second here. A power set is all of the subsets of the original set, okay? The power set of this room is every possible set I could come up with the people in this room. So there would be 16 that just have one person in them, right? 16 sets, one that has your name, your name, your name, your name. And then there would be one that has your name paired with everybody else, right? And so on until you have 2 to the 16th number of sets. The empty set, the power set of that is a subset of everything in the empty set. Well, what's in the empty set? Nothing. So the only subset of an empty set is the one subset that all sets have, which is the empty set. So the power set is all the sets, subsets, that are in the original one. The original one has nothing. So there's nothing to put in there except for the one set, subset, which is the empty set. So the power set of the empty set is the set that contains the empty set. Yeah.
So if you recursively took the power set of an element that only, of a set that only had one element, then you basically be constantly pairing itself with the empty set.
Yes.
And
So if
creating sets like outward.
Yeah, so if I had a set that contained just the letter A, the power set would be A, the set A, and then the empty set, and that's it.
And then you would.
And then if I did a power set on that, it would be the set that has A, the set that has the empty set, and the set that has A and the empty set.
And it would just keep going.
And if you kept recursively doing that, it would just keep growing, yep. There's all these things are things I want to now add to the slides because they help clarify the concept a little bit, so, yeah, very good. All right, let me get back on there, here we go. So what is the power, so this is basically the question. What's the power set of the set that contains the empty set? No, it's not the same thing. How many elements are in this set?
One.
There's one element, so it's gonna be 2 to the first power, which is 2 things. So what's that? So that's how many elements are gonna be.
The empty set, and then the set that contains the empty set.
Yeah, it's gonna be the original set and the empty set, right? Like that. Okay?
And then you take the power.
Don't try to recurse this, man, holy crap. Do it for fun, write a recursive program that keeps building the power sets. Remember, the power set is a set in and of itself. And by definition, a power set, all of its elements will be sets, okay? Every element of the power set will be a set. Every element of the power set will be a set. Every element of the power set will be a set, okay? All right, so how do we feel about this? This is deep stuff here, man, it's tricky. And that's another way to write it, same thing, okay? That's a little more messy if you do that, but it is the same thing if you look at it closely, okay? That's another way to write it. Okay, those are all three the same thing. We good with that? Okay, study these couple slides here for sure, okay? What are some uses of this? Why, who cares about a power set? I'll give you a silly use, but there's some other more practical ones. What if you own a pizza shop and you have 10 toppings? What is the power set of your toppings? What does that mean?
All the different types of pizzas.
It's every kind of pizza that could be made, right? If I have 10 toppings, I'm gonna have 2 to the 10, let's just go with 3 toppings. I'm gonna have 8 possible toppings, right? I will have pepperoni only, ham only, and jalapenos only, right? Then I can have ham and pepperoni, or ham and jalapeno, or pepperoni and ham, or all 3, or none, right? I got a pizza with none. So that power set is every type of pizza I could make, okay? But something a little bit more practical in the math world, and it's not like the pizza guys are back in the back room doing discrete math, figuring out their pizzas, right? Okay? But your database that contains things about your toppings and about, and maybe people doing some market research and finances and how much it costed to make certain pizzas certain ways, like, you guys remember $5 Pizza? Some of you are like, I've never heard of it. It was a college project where students had to create a business plan, and the business plan they came up with was that all pizzas would cost $5, no matter how many toppings you put on it. They're not in business anymore, but for a while they were huge. They did really well. It just inflation, the market, whatever, things changed, and there's still a few around, I think. But I could see some sort of analysis in the back end of how many toppings, how many types of pizzas would there be, how complex would it be, how much would it cost. I could see that in there. Okay, but here's where we see it in our world. Okay, we're going to be getting into combinatorics in a few weeks here. Combinatorics is very, very useful in our world. It helps us calculate the numerator or denominator for discrete probability problems. Okay, why do we care about discrete probability? Because discrete probability leads us into what's known as Bayes' theorem. Why do we care about Bayes' theorem? There are a million reasons why Bayes' theorem is important, but one of the big ones in our world, a good example is a spam filter is actually programmed based on Bayes' theorem. Bayes' theorem is used in the medical world to tell you what's the probability you actually have cancer if you actually get hit positive on a cancer screening test. We're going to look at some of those things. Yeah, it's not as high as you think it is for sure. We're going to get into that in a few weeks. But this power set thing can come in very handy with combinatorics. And discrete probability is easy. It's something divided by something, right? It's the thing that you want to happen divided by the thing that could happen. That's probability. It's not that hard. But how do you figure out what is the things that could happen, and what are the things you want to happen? You need combinatorics, permutations, and all this kind of stuff to do that. And that leads you, that this set stuff here is very useful for that, okay? So questions about that big picture idea?